All right, let's dive right in. We're about to explore what feels like a lost art form from the very early days of computing. It's a story all about raw ingenuity facing some truly insane limitations, and a programming technique so clever, it honestly feels like magic.
So let me ask you this, especially if you're a developer. Have you ever written code that writes other code? Maybe you've used code generators or messed with compilers. But this goes so much deeper, into a place that is just completely off the map for most of us today.
And that right there, that's our hook. This is a quote from a programmer named Octavio, who got his start way back in 1972. And listen to what he's saying. He didn't just write code that generated other code. No, he wrote programs that would actually reach back and alter their own instructions while they were running. Now, to understand why in the world anyone would do that, we got to take a trip back in time to the world he was working in.
So welcome to the early 1970s. The challenge wasn't just, writing a program. The real challenge was just surviving in an environment where everything was incredibly scarce. This was programming on the absolute frontier.
This right here was the entire battlefield. Octavio's computer, which was a 1972 DEC PDP-8 compatible machine, had a grand total of 16 kilopalabras. That's 16,000 words of memory. And notice he doesn't even say kilobytes. They didn't really think in those terms yet. Just to put that into perspective for you, 16 kilowords of this 12-bit memory is about 24 kilobytes. 24. Your average laptop today has what, 16 gigs? That's more than 500,000 times more memory. It's not even in the same ballpark. It's not even on the same planet.
And it wasn't just the memory that was missing. Forget about having an operating system to help you out or device drivers to talk to the hardware. In the very beginning, they didn't even have an assembler. The basic tool that turns human-readable code into machine code. It all had to be done by hand. So just picture this workflow for a second. First, you'd write your entire program out on paper. Then you become a human compiler, painstakingly translating every single command into ones and zeros. Next, you punch all those ones and zeros onto a long strip of paper tape, and you're not done. You then go over to the machine, and using these little physical switches on the front panel, you have to manually toggle in a tiny bootloader program, bit by agonizing bit, just to teach the machine how to read the paper tape you just made. It was just this incredibly physical, slow, and totally unforgiving process. So how on earth do you run complex, cutting-edge scientific analysis with just 24 kilobytes of memory and basically no modern tools? Well, you get clever. You get really clever. You invent a secret weapon, something we can think of as the binary shadow trick. Code that literally rewrites itself on the fly. The official name for this is self-modifying code. And just as it sounds, the program would actually change bits in its own upcoming instructions based on the data it was looking at in that exact moment. This let one single chunk of code act completely differently each time it ran, which, you guessed it, saved a ton of that precious, precious memory.
Okay, so let's see how this actually worked. Imagine a really simple instruction in the program, JMP76. Pretty straightforward, right? It just tells the computer, hey, jump your execution forward by 76 memory addresses. It's a fixed path, hard-coded right into the program.
But here's the catch. What if, based on the data you're analyzing, you actually need to go somewhere totally different? Let's say you need to jump to address 52 instead. Now today, you just write an if-then statement, right? Easy. But back then, an if-then statement was a whole new block of code, and you simply did not have the memory for it.
So here's where the magic comes in. This is the solution. Instead of writing a whole new instruction, the program would perform what's called a bitwise XOR operation directly on the existing JMP76 instruction right before it was about to be executed. By applying this very carefully crafted binary mask, it could flip just the right bits in the address part of that command, and boom, it would instantly transform JMP76 into JMP52. The program literally performs surgery on itself in mid-flight. Absolutely incredible.
And look, this wasn't just some clever parlor trick or an academic exercise. This was the key that unlocked absolutely groundbreaking scientific research. We're talking about work in a neuroscience lab that involved everything from complex statistics to experiments with cats and monkeys.
You can actually see their progress just by looking at their tools. They start in 72, hand-coding everything in binary. A few years later, their memory was doubled, all the way to 32 kilowords. That's just 48 kilobytes. And Octavia says they threw a party. A real party over getting 48K of memory. Can you imagine? And then later, when they finally got their first compiler, it was another massive leap forward, even if it was a quirky system that still involved feeding multiple paper tapes into the machine.
And all of that brutal, hard work, all of that raw ingenuity, it made some amazing things possible. Using these crazy techniques, they wrote programs to process brainwave data, to control the lab equipment for PhD-level research, and to run unbelievably complex statistics. They even managed to implement a fast Fourier transform, which is a cornerstone of digital signal processing, in 12-bit memory, using their own custom-made floating-point math. This was the absolute cutting edge of science at the time, all powered by code that rewrote itself.
So, what does this story about a lost art really mean for us today? Well, it's about a lot more than just old, obsolete technology.
The real lesson from Octavio's time is this: extreme constraints force a totally different kind of creativity. When you can't just throw more memory at a problem or import another library, you have to dig way, way deeper. You have to understand the machine at its most fundamental level and invent solutions that, frankly, should be impossible. Scarcity really was the mother of all innovation here.
And in Octavio's own words, this is a technique that's now lost to history. I mean, today, self-modifying code is a huge no-no. It's a nightmare to debug, it can be a massive security risk, but the mindset that it required, that deep, almost intimate knowledge of the hardware, that is something really, really special.
And that kind of leaves us with one last question to chew on. In our modern world of programming, where we have what feels like infinite memory and endless layers of abstraction sitting between us and the actual hardware, what have we lost along the way? What creative muscles have we just allowed to atrophy because we no longer have to fight tooth and nail for every single last bit? It's something to think about.